All right. Last week I kept mentioning this idea of radians. We are getting introduced to those radians today, and what I want to tell you is that radians are incredibly uncomfortable. And some people will fight it a little bit. And what I want to encourage you to do is embrace radians. So before we get into like exactly what a radian is, I want to kind of give you kind of a frame of reference for it, and that is in the United States. If I asked you to measure this board, you would probably be able to give me a decent estimate in feet, right? We think in feet. You could kind of give me what a foot is. Yes. If I asked you to estimate that width of that board in meters, you would hesitate. Yes. Okay. We are not used to thinking in meters. We're going to estimate like how wide is your table in centimeters. Not something we're going to be comfortable estimating in centimeters, is it? We don't think in centimeters. If I asked you what's longer, or what's the difference between 5 miles and 5 kilometers, do you know? Okay. We don't think in kilometers, do we? Has anyone been to a foreign country where they Canada? Okay, their cars, their speedometer is in meters per hour, not miles, and it will freak you out because you're driving at a normal pace, and all of a sudden it says you're going like 120 meters per hour, but you're not, because it's only like 60 miles an hour. But we don't think in meters. Okay. Now the reality of meters, centimeters, kilometers is that they're actually a lot easier to work with. But we won't raise them. Okay. If I ask you to do some calculations with meters or centimeters, they're so easy to work with. It's just a decimal to the nearest 10th. If I ask you to do calculations in inches, and now I got to think in fractions to a 16th, and that's ugly. But that's what we know. Okay. Well, the difference between meters and feet is like the difference between degrees and radians. It's just a different method, a different measurement length for measuring things, for measuring an angle specifically. Okay. And I'll tell you right now that radians are uncomfortable, just like us thinking in meters is uncomfortable. But ultimately, it actually becomes a lot easier. Force yourself to be uncomfortable at first, because eventually this year we will not talk degrees ever again. And the better and the faster you can get at radians, the better the semester will go for you. Okay, and some of you are going to fight me on this, I know that, but guys, I'm telling you right now, there are ways around having to know radians at the beginning here. Don't take them. Embrace the uncomfortable. Okay, so that's what we're going to start with today, these radians things. Just getting into our angle basics. First of all, when we talk about an angle, it is formed by two rays. If I go back to my geometry definition that share the same endpoint, one of those rays where we start the opening of our angle is referred to as our initial side. The ray where we stop our opening of our angle is called our terminal side. That point that both of the rays come out of, or the corner of our angle, is what's called our vertex. That's just from geometry. Most of the time here we will refer to that angle as theta. That is just a Greek symbol. That is a variable with angles. Typically they use theta. You can call it X. You can call it alpha. I don't care what you call it. It's a variable. Okay? But you'll see theta most often for our angle. Standard position, and this is what we will work with all the time, is our standard position of our angle. If I were to draw the X and Y axis, your standard position starts your angle at that positive X axis and opens from there. Now, if our opening starts at that positive X axis and goes up, that's the key, goes up first and is rotating counterclockwise, our angle will be a positive measure. If we start at that positive x-axis and head down first, heading in a clockwise direction, our angle will be a negative angle. And again, our starting position will never change. And a lot of times we won't draw the initial side because it's understood that it is the positive x-axis. What you will see drawn is the terminal side. And we will always just draw our terminal side. We'll start our pencil at that positive x-axis and go to our terminal side. As you are learning how to draw angles, or not learning, as you draw angles, one of the important things is that you actually have this curve with an arrow at the end of it to indicate which direction, because I could have started here and gone around this way to get to that line, or headed down. And so the little curve connecting with the arrow actually does become important to us as far as we're looking at the positive version that got us to that line or the negative version that got us to that line, right? And in fact, we can have versions that circle around our origin and then stop at that line. And that's kind of our conversation at the end of today, so we'll get there. Okay. All right. We kind of skipped our little activity at the beginning of today. That's supposed to introduce you to a radian. So here's what a radian is. If I were to say 1 radian. A radian takes the length, we all know the radius of our circle, right? It's this little straight line that goes from the center to the edge of my circle. If I were to take that little straight line and wrap it around the edge of my circle, where it stops, if I were to draw the other side of my angle through that, the angle that opens that wide to give me the length of 1 radius here is called 1 radian. That's why it gets the name radian, because it's the length of a radius around the edge of our circle. Okay? And so what you guys are looking at there is kind of an example of 1 radian. And what we're going to find out is that's not a great drawing because it takes me approximately just over 3 of those to complete a half a circle. What number do you guys know that's approximately just over 3? 5. No coincidence that circles and pi go hand in hand. Actually, that's where it comes from. And so you see that a half a circle will equate to 1 pi radians. And if so, if a half a circle is 1 pi, completing a whole circle would be 2 pi. That again comes from, if we were to consider our radius between the length of 1 unit, our circumference is 2 pi r, and if our radius is 1 unit, it's 2 pi times 1 or 2 pi. Okay? So that's where this next part comes from, and this is very important, is understanding that 360 degrees, which is what we're comfortable in, right? We know 360. If I ask you to draw 360, you draw me a circle, right? That's the same as 2 pi in radians. 180 degrees is the same as 1 pi, and 180 being half a circle, right? Or a straight line. So converting between degrees and radians uses this relationship that a half a circle or 180 degrees is equivalent to pi radians. And so it's like multiplying by 1, it's just converting our units. Okay? So if I'm going from degrees to radians, I will multiply this little x supposed to multiply by pi divided by 180. It's like multiplying by 1. All it's doing is switching the units on our number, because this is radians over degrees. And if I'm going from degrees to radians, I want those degrees to cancel. So I want a degree at the bottom cancel with my current number. If I'm going from radians to degrees, I flip that because this is degrees over radians. And I want to be able to cancel those radians. So if I have some number in radians, and I want my answer to be in degrees, I need that radians to be in the bottom. So this is pi radians. This is 180 degrees, and these radians will cancel. Those units of radians will cancel, leaving you with an answer in degrees, which is why we do 180 degrees over pi. Knowing which way that fraction goes will be on you. You will practice it hopefully enough to know which way goes with which. Starting here. Converting from degrees to radians. So I'll show you how we convert from degrees to radians. I reminded you at the top, if I want to go from something that is in degrees, always think of this. If I'm multiplying like a fraction, degrees over 1 times radians over degrees, and I want my answer to be in radians, I need those degrees to cancel, right? That label of degrees to cancel, so that's why the 180 is in the bottom. Multiply by pi over 180. Now let's talk about the practical way of actually doing this, grab your calculator. I'm going to multiply by pi over 180, but I'm not going to type this in. Don't type pi in your calculator. Grab your fraction function, it would be the best, or you can always use the math one to turn your answer into a fraction. But what you're going to type in is the fraction 30 over 180, or 30 divided by 180, and we're just going to simplify this fraction. So what I'm going to do is I'm going to take this pi that I didn't type in, and in my answer, I'm just going to continue to have a pi sitting in the numerator. And then I want to put around it this simplified fraction of 30 over 180, which is down to what? 1/6. Now, yes, I know you just said 1/6, so there's the 1/6, but 1 times pi is pi, so actually this will just look like pi over 6. Usually we don't usually write 1 in front of our numbers. Not wrong. You just don't usually see it. Okay. Question from the converting from degrees to radians. So now you understand what my label would be in the radians. You don't write radians. You write degrees with a little symbol. And if there's no little symbol for degrees, you get to assume that it's radians. Okay. So we're going to try these two. Ooh, that's a line. I'm going to do the next one with this. You see how it has a negative? We haven't talked negative yet, have we? Guys, if you are converting, it does not change your answer. And I don't actually type a negative in my calculator as I do this. You can. All I need to know is that if my problem starts out as a negative, my answer will also have a negative on it. Okay? So I'm going to go take this times pi over 180. I'm not going to type in pi. I'm going to type in 135 over 180 and simplify that fraction. I put the pi in my numerator already. I put the negative out front because my answer should be negative with my original answer. Angle part about negative. Okay, and what is 135 over 180 simplified? 3/4. 3 pi over 4. This would be negative 3 pi over 4. Okay, go ahead and try the last one on your own. This is just an example where we have a value bigger than 180. Keep it as an improper fraction. Do not write these as mixed numbers. Okay? So most of your calculators would do improper fractions anyway. But if your calculator were to convert it into a mixed number, you need to look at the improper fraction version of it. And again, that pi is just going to go sit in my numerator. I will not type pi into my calculator as I'm doing this. I'm just going to type in 300 over 180. Pi over 3. Right? Okay. Questions on that? Good on the calculator usage there? Okay. Going the other direction. Radians to degrees. Notice again, if I were thinking about some number that is labeled in radians, and I want my answer to be in degrees, I set up my fraction with the 180 and the pi, so the degrees are in the top, the radians are in the bottom, so that my radians will cancel when I multiply those two numbers together, leaving me with something labeled in degrees. Now, there are actually two different ways this will look. Going from degrees to radians, there's no variation on that. It looks exactly how we have every time. However, this one does it have pi or does it not have pi? Okay, so with pi in my original radians, what happens is as I multiply this by 180 over pi, the pi's cancel. With pi, pi's cancel. Okay, and so my pi on the top will cancel with my pi on the bottom. And then I'm just figuring out what 180 divided by 4 is. And 180 divided by 4 is 45. And I'm going to label it as degrees because I'm going towards the degrees answer. Okay, questions so far? think I only have one on this one. Okay. So what if it doesn't have a pi? So here's our second question here. We start out with something in radians that does not have a pi. We still multiply by 180 over pi. But this time we will type pi into our calculator and get an ugly answer. And we'll round. Okay? Do whatever we're instructed to let right now. But if there's no pi to cancel it, now I have no choice but to just type it into my calculator. So I would take 6 times 180 divided by pi. And I'm going to guess something. Is that 27.4? Okay, so that's your two variations on the radian. It either starts with a pi or it does not. We rarely see this. Okay, this is not very common, and the majority of the rest of our students will be looking at these numbers right here and knowing what that looks like. I know right now you probably can't visualize something that is a pi over 4 angle, but eventually you will know exactly what a pi over 4 angle looks like. We'll get there. So just know that you won't see this often, which is why we don't use calculators almost a ton eventually. So let's again see one with a negative in there. Going from radians to degrees, same thing, radians to degrees, I do the 180 over pi. Because there was a pi in there, I get to cancel. The pi crosses off here, and I can just type in the 4 divided by 3 times 180. You can type the negative into your calculator if you want to. You do not need to. All I need to know is that if my problem starts out as a negative answer, a negative angle, my answer is a negative angle. Okay. All right, what do we get here? Label it in degrees. All right, last one. Negative 4.7 radians. Looks like negative 269.3. See that right? All right. Questions? We don't do the converting often. Okay. You do need to know how to do it. Okay. We will use it more actually tomorrow than any other day. What we need to really embrace is this idea, drawing angles. Now, before I give you one, I want to add one little page in here, which you don't really need to have in your notes. But if I ask you to draw an angle in degrees, I do want you to make sure that you just kind of compare things. As we work our way around a circle, you would start at 0 degrees. This line right here, that angle right there would be how many degrees? 90, right? A right angle would be 90 degrees. So if my angle that they asked me to draw was something less than 90, I would put it approximately somewhere between 0 and 90 degrees, right? A straight line or another 90 added onto that would be 180. So again, comparing it, if I asked you to draw 130 degrees, you would obviously go farther than 90, but not to 180, right? Adding another 90 onto that because every corner is another 90, right? So then our line down here would be equal to 270 degrees. Again, finding something falling appropriately ultimately another 90 degrees, or finishing a full circle would be 360 degrees. They can ask you to draw things in the negative direction, which is fine. That means I would start here and head down first. If I were to head down first, that would make this negative 90 degrees, right? And you would just think those same values backwards. It would be negative 180, negative 270, and negative 360 okay? That I don't spend much time on because, again, that's something that we have a lot more prerequisite knowledge on, right? We're more comfortable if I ask you to draw a 90-degree angle, that we can all draw a 90-degree angle. Unfortunate, right? What we probably can't draw is a pi over 4 angle, okay? So let me give you my best advice for how to draw angles and radians. Think fraction. Every time I give you an angle and radians, here's the first thing I want you to do. I want you to go to half a circle and mark it as 1 specific to that base. So our base of this fraction is a 4. 1 would be 4 over 4, right? So this would be like 4 pi over 4. That's 1 pi. A full circle is always 2 pi, but I want you to always write that specific to the denominator we're using. So we are doing 4. This would be the same thing as 8 pi over 4, double the denominator. That's how you get 2, right? So think of it in the terms of that specific base, that over itself for half a circle, double that over itself for a full circle. Then basically what it's saying is, as I were to complete this half a circle, I'm going to split it into this many angles. So if I were to go all the way here, there'd be halfway, right? Split each of those into half. There's 1, 2, 3, 4 of those, giving me 4 fourths. Okay? And if I was supposed to draw 1 of those, I would go 1 fourth. There is a pi over 4 angle. Eventually, we're going to stop drawing that little circle and breaking it into the correct number of angles, but that might help you as you start this. Okay? 5 pi over 4. I currently have 1 fourth, 2 fourths, 3 fourths, 4 fourths drawn up here. 5 over 4 is 1 fourth more than I have a circle, right? So I would go 1 more fourth here. So my angle actually would go here's 1 fourth, 2 fourths, 3 fourths, 4 fourths, 5 fourths would go 1 more fourth. And that angle right there would be called 5 pi over 4. How are we doing so far in our radians? So if it's 1 more than my denominator, I'm going to go just past half a circle. Because the denominator itself would be half a circle. Okay, let's look at our next one. Our next one is supposed to be negative 3 pi over 4. So I'm supposed to head down first for the negative, right? Negative says head down first. Are you guys okay if I erase this picture? Okay. And I'm supposed to go 3 pi over 4. Well, 3 is just 1 less than our denominator. If I were to go start down first and get a half a circle, that would have been 4 over 4. I was only supposed to go 3 over 4. So I'm going to back it up a fourth. And I only go 3 fourths of the way there in the negative direction. Now, that actually is the exact same angle that we just had. In this direction, it was called 5 pi over 4. In the negative direction, it's called negative 3 pi over 4. It's the same way. We'll talk about that in a little bit. Right? And the last one I have for you is an example of more than a full circle. If this is bigger than double the denominator, it's more than a full circle, right? Basically, I keep adding fourths until I get to that. So, if I were to start this direction, there's about 1 fourth, 2 fourths, 3 fourths, 4 fourths. fourths. Now, if I were to get to this line again, I've now completed 8 fourths, and I was supposed to go 9, which means one more fourth. So I go one more fourth. To indicate that it is 9 pi over 4, I would draw the whole circle around and then get up to my 1/4, or total of 9 fourths. Hey, are you uncomfortable? No? Yeah, okay. It's like I told you, it's uncomfortable. Eventually, you're going to be able to fly right to those angles. I promise. Trust me. I've done this a lot of years. Okay? We'll get there. It's very uncomfortable today. This week. It won't be. We're going to do one more example to kind of help us. The typical ones that we will see are pi over 4, pi over 3, and pi over 6. You'll see those by far the most often. Because building our way to what this thing is that ultimately we're heading towards is called this thing called a unit circle, which is like the thing this semester. This unit circle. They use pi over 4, pi over 3, pi over 6. Okay. Could I today throw in like a pi over 12? Something pi over 2, something like that. Yes, absolutely. You follow the same process. But think in the denominator. So again, the first thing I want you to do is to kind of give yourself a frame of reference of how it relates. Is call this 3 pi over 3. That's 1 pi. Call it for a full circle, double the denominator, 6 pi over 3. Is 2 pi. But it helps me specifically think in thirds. Now, this is not as pretty as fourths because if I were to go and half a circle and break it into 3 angles, I would have one angle here, one angle here, and one angle here. There's 1, 2, 3, breaking it into the thirds. Notice we don't use that axis time. Okay, and that's okay. We don't need it. It's not a third. Okay. If you ask me to draw 1/3, I would only go one of those little marks. That angle right there would be pi over 3. As you're getting used to this, if you want to continue to go and do the bottom side of it and break it into thirds, you can do that. Like I could also do the bottom side here and go 1/3, 2/3, 3/3. So now here's all of your options. If you like that, then I can follow that for this next one. This is I'm supposed to go 5 of those, right? Well, if I'm supposed to go 5 of those little marks, there's 1/3, 2/3, 3/3, 4/3, 5/3. That will go to this line right here. That's 5/3 around my circle. 1 away from 6/3, 1 away from double the denominator, which you notice falls just short of a full circle. Okay. Let's go in the negative direction. Negative 2/3. I'm going to erase my marks and see if we can do it without my marks. If I'm supposed to go negative 2/3, again, negative means I'm going to head down first. And I'm supposed to go 2/3 of the way. Well, it only breaks into 3 angles, so this would be about 1/3. 3/3 would get me all the way to this line, and I don't want to go all the way to that line. 2/3 is farther than half, right? So go farther than half of the way to that 3/3. And there's my 2 pi. Negative 2 pi over 3 down first. Okay? So good? All right, now let's look at it bigger than a full circle. 8 pi over 3, 6 pi over 3 is a full circle. So obviously 8 is bigger than that. How much bigger than that? 2, right? So we need to go 2/3 past the full circle. So if I were to complete a full circle, I have now gone 6 pi over 3, and they asked me to go a total of 8 pi over 3. So I need to go 2 more thirds, right? So here's 6 over 3. This would have been a 7 over 3 angle. And again, I'm just having around these approximately, right? But approximately falling into the correct quadrant because 8 pi over 3 would have to fall 2/3 is more than half. So we go more than half of the way. There's 8 pi over 3. Had I gotten to this next line, that would have been 9 pi over 3 if I keep adding thirds, right?
How do you draw that with all the other like marks that are on here? Like, do I just
write? I would probably draw separate. I didn't have that much room. But really, I will be able to tell, like based on like I can follow those little scrolls in your little angles and everything. So the important parts of it are you are going the correct direction. So we've got the arrow indicating the direction we were going to get there. Heading to that line. Okay. All right. So there's your introduction to drawing is. What if I had a denominator of 6? I would think in 6 over 6 and 12 over 6. Right. Full circle would be 12 over 6. How do they relate to those? And if you want to go in and break it up into 6 equal angles, do that. Okay. All right. There's where we're starting. Now let's talk about this next picture because it's kind of what Sarah was just saying. We've got a whole bunch of angles on there and what's going on. You guys notice I got a whole bunch of swirls in that picture up there, but only one like line drawn, one angle. It's like that 45-degree angle you see that. They'll stop at that same one. It's just a whole bunch of examples of the same thing that all stop at the same line. You have 45 degrees stop at the line. Or down, that's 360, stops at that same line. Or I could have like done a full circle and stopped at the same line. That would have been equal to like 360 plus another 45 is 405 degrees. What you guys are looking at in that picture is this thing called co, meaning same, right? Co-workers are at the same place. Co means the same. Terminal means where they stop. They have the same stopping sign, or the same terminal sign. Okay, that's what it means by co-terminal angle. If they all stop at the same line, they're called co-terminal angles. How do we figure out what a co-terminal angle is? So when we got this idea right here, understand this underlying theme. If you add or subtract full circles to what you got, it's going to stop at the same place, right? A full circle will just get me back where I started. Now, a full circle will look a little different if we're talking degrees versus radians. So we'll look at that here as well. What they look like side by side, but it's the same idea. Is you're just adding and subtracting full circles to end up at the same line. Again, will become very important to us fast forward to this thing called the unit circle that we will get to next week, which is where this is all building up to, is this big thing called the unit circle. Okay, so I'm going to give us 2 examples here. One, finding co-terminal angles in degrees, and then the last example we have today is us finding co-terminal angles in radians. Now, we do the same exact thing. We add or subtract a full circle. So let's look at what that looks like. In degrees, a full circle looks like 360 degrees, right? Again, going to be more comfortable with you today. Eventually, we'll get to the radians being fine. So if we started with 400 degrees, first of all, 400 degrees is more than a full circle, isn't it? Like how much more than a full circle? 40 more degrees, right? 360. So how much past 360 are we? So if I were to draw that, that's kind of what I think about as I'm drawing that. It is more than a full circle. So I start with a full circle. And then I would draw the difference between a full circle and 400, which is 40. Well, 40 is going to fall somewhere between 0 and 90. So 40 degrees would be like right here. That green angle right there is 400 degrees. There's a picture of 400 degrees. Okay, so let's look at a positive and negative coterminal angle. Now, the easiest way to find this is just go in the positive or negative direction. A positive coterminal angle can be found by taking our original and adding a full circle. So plus 360. 760, right? Good. Okay, so what does that look like? Well, 760 is like 2 full circles. 360 times 2 is 720. So that's 2 full circles and then 40 more. So I would draw it like this. 1 full circle, 2 full circles, and then 40 more. That's a picture of 760 degrees. Okay, I strategically picked 400 for the negative coterminal angle, and we're actually going to see how that is. Our process starts out by giving us a positive coterminal angle. To find a negative coterminal angle, you take your angle and you subtract a full circle. But you need to get a negative answer. Well, 400 minus 360 is a positive number, isn't it? This is not a negative coterminal angle. That's actually an example of another positive coterminal angle, like 40 degrees. is another positive coterminal angle. So I continue the process. So I must repeat subtracting a full circle. So now I'm going to take that 40 and subtract 360 again. And if I have to keep repeating that, I keep repeating it until I get the sign that they were asking for. They were asking us for a negative coterminal angle. I keep subtracting full circles until I get a negative number. Same thing in a positive direction. If I added a full circle and I didn't get a positive number, I would add again and add again and add again until I get a positive answer. It's just meaning the direction you're supposed to be headed. So 40 minus 360 would be what? Negative 320. That's a negative number. That's a negative coterminal angle. Negative means I head down first. There's negative 90, negative 180, negative 70, negative 20 would fall short of a circle. All of my lines should look exactly the same if I did this correctly. That's what makes them coterminal. Question. Again, I know right now our building blocks seem very random and disjointed. They will all come together next week as we get into this thing called the unit circle, but there's so many foundational steps getting there. It takes us like a week to build up to it, okay? All right, last one. Same exact question, but in radians, okay? If you are good at fractions, radians is a little bit easier for you because you need to think fractions. So, same idea. Oops, I said add 360. Let's not add 360. Let's add 2 pi with the correct denominator. Isn't 2 pi the same thing as 360? So it's okay that I crossed out the 360 and 60 pi. It's a full circle. Okay. Well, what is that? If our denominator is 3, 2 pi is the same thing as 6 pi over 3, right? Make it specific to your denominator. And I will always show it that way. So if our angle is negative 4 pi over 3, I'm going to add a full circle. And the reason I get them to have the same denominator is because they're fractions. I have to have the same denominator, add them together, and now I can just add the numerators because they have a common denominator. Negative 4 plus 6 is 2 pi over 3. Oh, I forgot to draw the 4 pi over 3. Negative 4 pi over 3. Heads down first. Thinking in radians or number, I have a circle of 3 pi over 3. A whole circle is 6 pi over 3. And it's time to go 4 pi over 3 heading down first. A half a circle would be 3. And I'm supposed to go to 4, which would be 1/3 more. So I keep going 1 more third. All of my angles should have that exact same line. How do I get there? So my 2 pi over 3 should have that same ending line. Well, if I think about 2 pi over 3, there's 1/3, 2/3 when that ends right there. I have that direction. Okay. All right, let's do our negative. Negative 4 pi over 3 minus a full circle. Again, common denominator allows me to just add my numerators together. 4 minus negative 4 minus 6 would be negative 10. That's bigger than a full circle, right? Because a full circle would be 6 over 3, and we're looking at 10 over 3 in the negative direction. We should anticipate that our line ends here. So if I head in the negative direction and I go full circle, there's 6. Another third would be 7. Another third would be 8. Another third would be 9, which would put this line right here. And another third would be 10 pi over 3. Negative 10 pi over 3. All right. At this point, I have some people say, well, can't I just, so maybe this was you, can't I just go back to the beginning and like convert 4 pi over 3 into degrees and then add 360? Absolutely. Absolutely. Don't do it. Okay? You 100% will give you the right answer, but this is exactly the moment I'm talking about. Embrace the uncomfortable. It is uncomfortable to think about how to draw that angle in radians, absolutely. But you got to learn how to draw. So do it now. Okay, do it now when we don't have a lot of other things depending on it. And bear with me as we do this. Okay. All right. to kind of skip this here. Can we go to step 3? Can you guys go draw me please a 7 pi over 4 angle? Draw me a 7 pi over 4 angle. Seven pi over 4. Embrace the uncomfortable. All right, we're doing good, guys. We're doing good. Again, I know you're getting annoying when I'm saying this, but embrace it. I promise you, it will get easier. I promise you, you'll be way happier with yourself if you force yourself to just focus on the tool. What does radian look like? So then when I fast forward next week and ask you to find the cosine of 7 pi over 4, just figuring out where 7 pi over 4 is not the hard part for you next week. Okay, so take that part out of it. Get to know those angles, get to know what they look like. One more time, think in the denominator. So half a circle will always be 1, 4 over 4. Full circle will be double the denominator. We are supposed to go 7 over 4, which would be just short of 8 over 4. So if I follow my rules here, now it's an even number of half is going to be 2, right? There'd be 2 over 4, 4 over 4, 6 over 4, 7 over 4 would put me into that 4th quadrant right there. There's my 7 pi over 4 angle. Okay. Your assignment tonight is a worksheet. Let me get that out to you. We will run 3 directions here real quick just so you make sure that you are clear on what is supposed to be going on your worksheet. Okay, on the front side it says draw each degree in radians, each degree measure in radians as a multiple of pi in each. So it doesn't tell you each one specifically, but obviously if it starts in degrees, your answer is in radians. If it starts in radians, your answer is in degrees. Okay, so just go to the other one. Leave your answers exact except for like number 4. Number 4 is the only one that you will have a decimal for. Okay, so number 4, you'll have a decimal. Everything else should be either as like a fraction with pi or a degree. And then on the back side, you are giving me coterminal angles. So you're going to give me your answer now. Whatever it starts in has to be the same as your answer. So you'll notice on part A, it starts in degrees. Your answers must be in degrees. On part B, it starts in radians. Your answers must be in radians. It is not going to be in your best interest to convert the radians to degrees and then convert back. Don't do it. Just force yourself to work in radians. And you'll draw a picture of each of those. You now have to draw the original angle. Just a picture of the positive coterminal and the negative. All right, when you are done with these, they will get submitted onto Google Classroom. I am going to go put up a